Hello, welcome back. Let's go ahead and take a look at row and column spaces of a matrix. So before we get started with this example, I want to write down the definition of these things. So A is an m by n matrix. And then formally the row space of A is defined to equal the span of the rows of A. Right, so we take every row has n entries, how many columns there are, so this is a subspace of R to the n. And then the column space, which is defined to be the span of the columns of A naturally. Well, every column has m entries in it, so this is a subspace of R to the m. And given that they are subspaces of something, this means they have bases. All right? So often, instead of just saying, okay, well, the row space is the span of the rows, and then walking away, we want to be specific. What does the span of the rows look like? Is there any redundancy? Can we write down a basis? Let's go ahead and check this out. Alright, so let's go ahead and take a look at this example where we can find a basis for the row and column space. So the book, you'll see one way of doing this, and really for the row space, we're going to stick with that way. The column space, there are two ways that we can go about it because it's not as straightforward as the row space. So, that being said, we'll start with the row space of A. All right, and we notice we have our three rows here. So formally, we could say that this is the span of our three rows, minus 3, 0, 3, 1, 1, 1, minus 2, 3, and 0, minus 3, 3, 0. So this might not be the most insightful because maybe there's some redundancy, maybe we don't have linear independence. So let's go ahead and take a look at the reduced row echelon form, and we notice that as we row reduce this, we have three independent rows. So the row reduced version, there's no way to write any of these rows as a combination of the other. So these three rows are independent. And the way that we got these is just by adding and scaling versions of our original rows. So actually, we didn't change the span at all. So a basis for the row space is always going to be the collection of the non-zero rows in the reduced row echelon form of A. So in this case, we have 1, 0, minus 1, 0, 0, 1, minus 1, 0, and 0, 0, 0, 1. And these three rows are independent, again, because we can see clearly we're not going to be able to write them as a combination of each other. And so therefore we have a basis. So again, as I was saying, the row space is easy. Just take the non-zero rows in the reduced row echelon form. Let's, on the other hand, take a look at the column space. Let's see, what color do I want to go with? Let's go with this weird yellow and we'll try it out. So the column space of A is, again, the span of the columns. So minus 3, 1, 0 is our first column. Our second column, 0, 1, minus 3. And then we have 3, minus 2, 3, and 1, 3, 0. All right, so off the bat, we know that we have some redundancy because this is a subspace of three-dimensional space, and we have more than three vectors. So that's not possible. All right, so how do we pick out which columns are important? Well, one way that we can do that is to take a look and notice that our reduced row echelon form tells us, let me erase all our row space stuff. Reduced row echelon form tells us that this third column, which is right here, here we have the reduced version and the original. This original version is -1 times the first column plus -1 times the second column, and that's how we get the third. So there's redundancy with the third column, so we're going to cross it out. Okay. Alternately, what's happening is that this is the column with the free variable. And that's why we're crossing it out. All right. And that's where the redundancy is, and everything that's left over that has a leading one instead of a free variable, we're going to keep those. So really, our basis, a basis for the column space of A is everything -3, 1, 0, the first column, the second column, but not the third column. Let's fix this so that we're writing down the right thing. So -3 and then 1, 3, 0. That third column again is a redundant column. All right. So there we have it. That's how you find the basis for the row space. So let's summarize that similar to how we did for the row space. So this is the columns of A, not the reduced echelon form, of A corresponding to the free variables. Or wait, non-free variables to the leading ones, let's say. I want to get this right. Right. So our basis for col A we can get by looking at the columns corresponding to the leading ones. All right, and this is going to be consistent, and that's one way to go ahead and get the column space and the row space, particularly bases for these values for a given matrix. All right, have a good one. Bye-bye.